Okay, today we're starting, you could say a new topic, it's combined gas law, which just like what you would guess, uh, taking two different gas laws and combining them. Okay, so one of the aspects that will be utilized is your activity on Thursday. Okay. So what that means is when you see activity over there twice, we'll have you work through it on your own on Thursday. Then we'll have some of the elementary students come down here and you can illustrate your brilliance with them. Okay? So on Friday.
We make a motion?
No. No. You're dealing with you could say Charles's gas law, the combined one. I just think Charles's makes more sense. So that's something that we'll be working on down the road. But with the combined gas law, okay, as I said, page 374, okay, that's where it actually starts talking about the combined gas law. If you choose, you can go ahead and read through a lot of that material. Sometimes I think it just makes more sense to give you an example of the problem and then move forward from there. Okay, there's a sample problem on page 375. Okay, we'll leave that up to yourself. We can just read through it. It says a helium-filled balloon has a volume of 50 liters at 25 degrees centigrade and 1.08 atmospheres. Okay. What volume will it have? 0.855 atmospheres and 10 degrees centigrade. Okay? So when you have your given amount of information, it tells you to, do you have to do anything with the pressure?
No.
You're correct. Why not?
It doesn't say anything about it.
Sure it does. It gives you the pressure.
Well, that's why you don't have to do nothing about it.
Well, that's true. But how's it labeled?
ATM.
It's in atmospheres. What do you need your pressure to be? In atmospheres. You're not always going to be given the pressure in atmospheres. You may have to make that conversion because temperature is different. It gives you 25 degrees centigrade and 10 degrees centigrade. But that's not what you have to do with that to plug into there. You need to have it in kelvins. That's why they illustrate adding 273 to that. All right. So it says the volume. Now we'll just move ahead and go on to the practice problems on page 375. There's two of them on there. So with that, the volume of a gas is 27.5 milliliters at 22 degrees centigrade and 0.974 atmospheres. What will the volume be at 15 degrees centigrade and 0.993 atmospheres? That's why you're looking at a volume, a temperature, and a pressure. Hence, put two gas laws, combine them, make it the combined gas law. Because what have we learned so far? What was your first gas law?
Oil.
Okay, which was volume 1 times pressure 1 equals pressure 2 times volume 2. Okay? Then we moved on to Charles's gas law, and that formula was volume 1 times temperature what? 2. Okay? And then now you have T1 times V2. Okay? Now, the reason that's important is those 1s and 2s, what's the significance of them? Well, I know they're different numbers. Yeah. Right. So your initial conditions are the 1s and your final conditions are the 2s. Okay? So one of the things that you can do what's happening if the pressure is increasing in a gas according to Boyle's law? What's the volume doing? Volume is decreasing. Okay. Then what happens to the why would the volume be going up in Charles's law? What must the temperature be? the temperature is going up. Okay? So I don't really know. I haven't checked the tire pressure in our vehicles lately because it has warmed up quite a bit. But one of the things that you'd want to do is try to keep your PSIs approximately the same value. And I don't know, I think we run ours around 35 PSI for each one. Sorry? Okay. All right. So now, when you take these two, you combine them, hence that's where it gets its name. So CGL. You have your initial conditions. Setting equal to your final conditions. Okay? So we've read the problem, just like what you did in physical science. What is the best thing that you can do for yourselves? Okay? Write down the information that you know. Okay? And with this, because what it says is the volume of this gas, the temperature and the pressure, what will the volume be? Okay? So that means obviously you're changing them to your final set of conditions. So whether it's in milliliters or liters, it really doesn't matter because you can convert between them really, really easily. Let's say if the answer is supposed to be in liters, but you left it in milliliters, even at the very end, you can just switch it by multiplying by 1,000. If it's in liters and it's supposed to be in milliliters. All right, so we have a first temperature, a first volume, and a first pressure. Then it says what will it be when you change these conditions. Second pressure, second temperature, and then, okay? So it really doesn't matter which one of these you start with first. Just I highly recommend you don't get your initial conditions mixed up with your final ones. So it says the volume of the gas is 27.5 milliliters. So there's your first volume. Okay, and then it says 22 degrees centigrade, adding 273, 295. Okay, and then what's your first pressure? It's 0 point something, right? 974 atmospheres. Okay, then it goes on to state what will the volume be? At 15 degrees centigrade.
993 is your pressure.
Okay. Okay. So 15, that's what, 288?
Yep.
And then we don't know. It's asking what will the volume be? Okay. So just like in physical science, now you just do what the formula tells you to do, and then use your algebraic skills, right? All right, so we got volume 1 and pressure 1. So here's your equation. Volume 1 is 27.5. And your first pressure is 0.974. All divided by your first temperature, 295. Okay, and set it equal to what your new set of conditions are, which is on the right-hand side. We've got 0.993. Times 288. Oops, oh, that's not right. Oh, I was going to write a T on there, and that's a V. Okay. Okay. All right. So, not that you want to deal with the fractions, I would agree. What is the best thing? You're a mind reader.
Multiply it over.
Well, just get rid of your fraction. Okay? So then, what we could do, that probably won't show up very well. What is a number times a variable? Gives you that number and what? Sorry? If you take a number times a variable, it gives you that number and the variable. But you can't forget about 0.993. So we've got 295 times 0.993. $292. Okay, I think we've had our fun. Please stop. We're juniors now. Let's act like it. All right. So then we cross multiply here. You're going to do the same thing to that side. 27 and a half.
26.3337.
It's too dark in here. This, okay, 227.5 times 0.974 times 288. It's probably what you said. Okay. Was that the answer or what was on the right side? Oh, okay. So 7714.08. Okay. Have we left anybody behind? How we got from the problem to here, then to here. Yes, this is time consuming. I understand that. So then, how do you get V2 all by itself using your algebraic skills? You divide each side. That's right. So dividing that by 292.94. Okay. Okay. Pretty. Could be. Okay. Whatever works for you, just do that. Okay. You can pass that. Well, you can get that information from him later. Okay. All right. The second problem, can we move on past this one? Okay. Because the second one is just a little different because it's asking for the pressure to be solved in a different label. We'll get to that in just a moment. Because it says in practice problem number 2, a 700 milliliter gas sample at STP is compressed to a volume of 200 milliliters, and the temperature is increased to 30 degrees. What is the new pressure of the gas in pascals? Okay.
Practice question number 2.
Practice problem number 2. Okay. So. We don't need that. You're not talking about Dalton's partial pressure of gas laws, are you? Oh, well, maybe they are. Okay.
Mr. McKinney,
Yes, sir.
you don't know the voice.
I do.
Pretty good dude.
We're not concerned about that right now. Okay. So then, when it says what is the new pressure, we can presume that that is pressure number 2. Okay, so we'll go ahead and put a question mark there because this one's worded kind of tricky, right? Because it's dealing with STP. And unless you know what that is, you were told that, but we probably didn't say you've got to know this. Standard temperature and pressure. Okay? So we have a 700 milliliter gas sample. So 700 milliliters.
200 for your,
Okay? And then, okay, it's compressed to a volume of 200 milliliters. Okay? That's right.
then you gotta add 273.
Now, don't use that analogy we were talking about earlier where the pressure's going up and the volume's going down, or the temperature's going up and the pressure's going up. That does not work for the combined gas law.
One is 273.
Okay? Okay?
And how do you
So,
do that?
with that, it says a 700 milliliter gas sample at STP, which means, like you pointed out, at standard temperature and pressure. The standard temperature is what? 273. Okay? And then when we talk about the standard pressure, that is what? Okay, 1 atmosphere. Okay? So then there should be one other variable left, which is it's increased to 30 degrees centigrade, which adding 273 gives you 303 degrees Kelvin. Okay? Any questions about how to get these set up?
Seems quite simple.
Okay? But the problem that could present itself, what's the question asking to be solved in, though? In pascals. So once you solve for this, what's this pressure going to be in? No.
No, it's going to be
Well, it'll be in atmospheres.
No. It's going to be in atmospheres. So once you find that,
101.32.
and then, yes, that's still not right. You got the right idea, but that's kilopascals. They want it in pascals. Okay? Well, you solve for it in kilopascals first, then multiply that by 1,000. Okay? So, in other words, you should get 3.94 times 10 to the 5th. Let's just let you work on that first. 3.94 times 10 to the 5th pascals. Do you want to work on that on your own, or do you want to work on that together? On your own. Okay. Well, get started, and then we'll see how you do. Well, show your brilliance. What's that?
What your pressure 2 is? Did you tell us that?
I did not. That's what you're solving for. Okay, we'll go ahead and get rolling again. So this was the prior problem. Okay, so we got our equation. We have our setup. We got 700 that goes up on top. Okay, and then we can just have 1 there. You could just have left that at 700 if you wanted to. Okay, your first temperature was 273. Okay. Then when we get over to this side, we've got 303.
Mr. McKinney?
Yes. Oops, that's on the bottom. That is not right. Goes down here. Okay. 200, and then pressure 2. All right. So again, whatever works best for you. If you can, this is how I do it, and this is how we're instructing you to do it. And if you find a different way that works for you, go ahead and do that. But this is possibly what I think is the best way. It's not the only way, but it's probably the best way. Okay. Why?
Very uncalled for.
Triggered by PTSD.
Okay. Like I said before, we are 11th graders. Let's act like 11th graders. All right. Do I need to repeat myself?
Once again.
We are 11th graders. Let's act like 11th graders. Okay? Yes. All right. So, how do you get rid of your fraction?
No.
You cross multiply. Take 273 times 200. And upon doing that, 273 times 200. And you get 54,600. And times your variable, or P2. Then 700 times 303.
21, 21, double zero.
Okay.
Mr. McKinney.
212, 100. Just a moment. Sorry?
Care if I step out?
Yes, sir. Go ahead. So now, again, just like what we did before, dividing each side. Okay. Are we all excited to play Castlewood tonight, right? Can't wait? Well, good. Just a question. No, I think you're just fine. So 212,100 divided by 54,600. And then that gives you 3.88 atmospheres. Again, that's in atmospheres. We want it in pascals, which convert it to kilopascals first. So 3.88 times 101.325. Okay? And that gives you 393.14 kilopascals. But notice, we're looking pretty similar, but to get from kilopascals to pascals, you multiply this by what? 1,000. Okay? So, which means you have to add on another 0. Okay? And these are pretty close to one another. What the author has done is put these in significant figures, but this is the answer we're looking for. All right. Questions on that? Because it's not that we're saying you've been forewarned. This is more so not a warning that, oh my gosh, this is going to get difficult. It's just saying, okay, we're not choosing to make this difficult, okay? It's what the author moves on to say after this. We'll be dealing with the ideal gas law, which includes your good friend stoichiometry again.
Yes.
Okay? So what that means is, we can cover that some other time. Because there's a constant that you use in these mathematics. What might be a constant value that you've used in the past in physical science? 9.8, that's the acceleration due to gravity. That's when that is dropping. What might be another constant that you would use as far as finding circumference? 3.14. So these constants that we use are not just for pure mathematics, they're also used here in that of chemistry. So that's all I have. So tomorrow you get your next paper. We'll also talk about your activity that you'll be doing on Thursday. We'll be in the lab. Okay. Yes, sir. We'll catch up to you next time.